Previously, we solved the problem of when aphid growth rate and predation by a ladybug are exactly equal, and we did it for the special case of n equal 2. And the solution in the case n equal 2 could be arrived at by a quadratic formula. In other words, it could be written down explicitly. That solution represented these 2 points of intersection of the 2 graphs, and there was also a solution at x equals 0. Today, we address the problem of what happens when n is some other value, for example, n equals 3 in the Hill function. In other words, we're looking at a predation rate which has a form shown here. Its structure is going to be very similar with perhaps a slightly longer lag phase in the beginning. And the question is what to do. Well, we can still carry out a few of the same steps. We can set these two to be equal, and we can still cancel out a factor of x, meaning we can say either x is 0, or if x is not equal to 0, cancel out a factor of x and arrive at r equals kx squared over a cubed plus x cubed. This in turn can be written in the form r a cubed plus x cubed equals kx squared, but now we are going to arrive at a cubic equation. Notice that the highest power of x here is x cubed. There's no convenient formula for the solution of this type of equation. However, we can write this as rx cubed minus kx squared plus ra cubed equals 0. Now we've written it in a form that makes it ideal for the application of Newton's method, because in fact Newton's method will allow us to numerically find good approximations for these points, even if we cannot write down the solution algebraically using pen and paper. And the idea is going to be that we will define this whole thing to be a new function f of x, and we will use Newton's method to solve for x in f of x equals 0.